This week's session is all about waves and optics, and we'll be looking at these questions from the Isaac Physics board. Some of these involve drawing a diagram and then typing in answers that you've read from the diagram. So you will need plenty of paper to do these questions. 38.3, you use the two most basic equations for waves. The wave speed is the frequency multiplied by the wavelength, and the frequency is the reciprocal of the time period. Just be careful to check your units, particularly for wavelength. If it's given in a unit other than meters and your frequency is given in hertz, then you'll get a speed that's in something other than meters per second. If your wavelength is given in meters and your frequency is given in hertz, then your wave speed will be given in meters per second. If your time period is given in seconds, your frequency will be given in hertz. So make sure you use these standard units. 38.19 uses the same equations as 38.3, but you do need to know those unit prefixes, those multipliers. For example, gigahertz would be 10 to the power of 9 hertz, or billion hertz. Megahertz would be 10 to the power of 6 hertz, or million hertz. And actually 38.20 is the same. There is another piece of information you need for these two questions, and that's how fast the wave is going. And for radio waves, microwaves, or any part of the electromagnetic spectrum, the speed of the wave we usually give as the letter c, which is 3 times 10 to the 8 meters per second. That's the speed of light, and it's the speed of all electromagnetic waves. That won't necessarily be given in the question, that's something you just need to know. 39.5 is about reflection from a plane mirror, and the usual way of representing a mirror is as a straight line with some hashing on the side that is not reflective, and the straight line is on the side that is reflective. Now if we take some object, such as this, which reflects or emits its own light, then that light will travel in straight lines, and we can represent that as a series of rays. And in truth, there's going to be an infinite number of rays emitted in every possible direction, but we're just going to pick a few of them for the demonstration here. Rays would be straight lines, they would touch the mirror as well as the object, and they would have an arrow indicating the direction that they're moving, or that the light is moving. Now the light will always reflect off the mirror, so that the angle of incidence, which is the angle between this normal line and the ray, the normal line is 90 degrees to the mirror, that's what we mean by normal, so that's the angle of incidence. The angle of incidence will always equal the angle of reflection for a plane mirror. And I can represent those with the letter I and the letter R. And that's true for any ray that's incident on a mirror. If we were to draw a second normal, such as this, you'll be able to see that the second ray, the green ray here, is also reflected, so that the angle of incidence for the green ray is equal to the angle of reflection for the green ray. Now if you extrapolate those rays back, you'll see that they seem to originate from a point here, and that point is what we call the image. That image is the same distance from the mirror as the object is, and a line connecting the image to the object would pass through the mirror at 90 degrees. It would be normal to the mirror. This image is referred to as a virtual image, because the light doesn't actually come from here, it comes from down here. There is no light passing through this image, but it is nonetheless the point from which these rays appear to diverge. If we were looking at this picture from over here, here's our eye looking from down here on the right hand side, then we would not realize necessarily there was a mirror there. This is the idea of most magic tricks. We wouldn't know there's a mirror there. We would think that the object was up here somewhere, where in fact it's not an object, it's a virtual image. Now 39.5 is going to ask you to draw a diagram for a particular situation and then make some measurements from it. You don't have to make measurements. You can use geometry, trigonometry to work out what some distances it asks you to measure are. This is generally called geometric optics because it's so important that you get your geometry right and you draw the diagram correctly. My clue for this one is draw the diagram large and as accurately as you can so that you can make those measurements from it. 44.3 is a tricky question and it's not included on many exam boards, so I'd understand if you want to skip it, but have a go at it. It's about diffraction, with spreading out of waves after a gap. So if you imagine waves coming in like this, and I'm using these lines to represent wave fronts, you might have to look up what a wave front is. They diffract, so the waves can spread out after they've come through this gap, and it has a certain angle through which those waves are spread. We can call that theta for now, a diffraction angle. And what you'll find is that if the waves have travelled through a wider gap, that diffraction angle, that angle through which they've been spread, is actually less. The narrower the gap, the more the waves spread. The wider the gap, the less the waves spread. And the relationship is lambda over d. This is somehow related to theta. For small angles, you could say it's proportional, but for larger angles, you can say it's proportional to the sine of theta. Now that's all very complicated. You don't have to worry too much about that. A larger angle, theta, means a larger sine of the angle, theta. So let's just say there's a relationship between that and theta. And I don't have a nice symbol to show there's a relationship, so I'm going to invent something. There we are. Some sort of relationship between that. If lambda over d gets bigger, theta gets bigger. If lambda over d gets smaller, theta gets smaller. So if these two pictures on the left and right have the same lambda, the same wavelength, and the d on the right hand side is bigger, then because the denominator of this fraction is larger, then the angle, the diffraction angle, is smaller. In the question, you'll look at a table of different wavelengths and aperture sizes. Aperture means hole or gap. You'll use a table of different wavelengths and aperture sizes to determine and rank what the diffraction angle, the order of the diffraction angles, which one has the biggest, which one has the smallest, and so on. 45.2 is all about seismic waves, but actually it's not that difficult. You're given enough information to be able to work out the answers yourself. Although it's not easy and there are a lot of parts to the question, it's really about geometry, trying to visualize what's happening, which path is longer, which one is shorter, which one takes the most time, and so on. Remember that P waves travel faster than S waves, but you don't have to know much detail about P waves and S waves to be able to answer these questions. But remember there's that hints tab if you need some extra help. The important thing with 45.2 is check the units, and remember the multipliers, these prefixes from the previous questions, you're going to need to know those as well. For the last question, 48.1, it might be easier if I just show you the diagram. So on this question, you will have to draw the ray diagram, drawing it very, very carefully. And then it says, state whether the image formed is real or virtual. You'll say, where is the image? What size is the image? Is it upright or inverted? Is it real or virtual? And that's the same for all these different situations. So in each of these situations, in the first one, you will draw the u, the distance to the object from the middle of the lens is u. You'll draw that to f. That's twice the distance as the focal length, which is the distance from the middle of the lens to the focal point. There's a lot going on here, a lot to teach. So if you in one of these questions, click on the hints, any of these hints, and go into notes on convex lenses. You'll see all the notes about what U is, F, V, what all these letters mean, and you'll be able to look at the lens equation, which doesn't appear very often. I don't think it's in the GCSE, it might be in the IGCSE, but you can look at the lens equation, although you don't need that for these questions. It might give you some more familiarity with these letters. And also we can go to magnification, which I think does come up, the idea of how big the image is compared to the object. Magnification, image height divided by object height. So all the notes are here for you to self-study, because there's a lot going on in that. But basically for each of these questions, you're going to have to draw the ray diagram very carefully. Now if you do a Google search for a website called PHET, I think that's how people pronounce it, P-H-E-T, you'll find this website. And you might have to click simulations for that to come up. Under simulations, you can click physics. And when you're on the physics simulations page, you want to scroll down, all the way down to the one on lenses. all the way down. I mean, it might be quicker just to search for it, but it's called Geometric Optics, and you want to load that one up. And when you load the Geometric Optics one, it looks a bit like this. You might have to, let's just scroll down to show you, you might have to allow Flash for it to work. Click on the little padlock and choose allow, and you do so at your own risk. I'm not going to be sued if it does something funny, but it's never done anything funny for me. But this is a lovely little simulation where you can move an object around and see what the effect is on the image. So you can see what happens. The image is on the right, the object is on the left, and you can see what happens. And you can choose to view virtual images. You can have a screen instead, but you can choose virtual images and see what happens when the object comes even closer to the lens like this. That's a virtual image. That's a real image. But in doing so, you can see these three principal rays that are drawn. So do a search for PhET, look for Geometric Optics, and you can play with this to really get a feel for how these rays should be drawn. Once you've understood how the rays should be drawn, so place the object so one side is on this axis down the middle, the principal axis, and this ray is always parallel to the principal axis. This ray always passes through, if you get it in the right place, there you go. This ray always passes through the far focal point and near focal point. This appears to have gone a bit funny actually, but never mind. There we are, that's better. If you play around with that, you'll get a real good feel for how images and objects work together. So I would recommend that. This question could potentially take you a long time, so do take your time with it, do your best, make sure you use those hints tabs to help you, and good luck.